Hello everyone. In today's lecture, we are going to discuss about the interrupts of 8086. What is an interrupt? So interrupt is a method of creating a temporary halt during a program execution is taking place, and it performs certain tasks which is being given by a peripheral device. So interrupt normally when a main program is getting executed or a core program is running, whatever task has been coming in between or task given by certain peripherals will act as an interrupt. Microprocessor responds to that interrupt with the interrupt service routine. So we have the main program and the interrupt service routines. So whenever a microprocessor wants to respond an interrupt, it runs the interrupt service routines instead of main program. There are different types of interrupt in 8086. Interrupts can broadly classified into hardware interrupt and software interrupt in the context of 8086. Hardware interrupt can further be classified into maskable interrupts and non-maskable interrupts. So now let us look into hardware interrupts. Hardware interrupt is caused by any peripheral device by sending a signal through a specific pin to the microprocessor. So this hardware interrupt involves hardware component. So see, this is the pin diagram of 8086 for your reference. Already we have discussed about the signal description or the pin diagram of 8086 in detail in the previous videos. So here I've given you a diagram for your reference wherein the pin 17 and 18 here acts as interrupt pins. One is non-maskable interrupt and next one is interrupt request. Along with that, here we have pin number 24, which is an interrupt acknowledgement pin. So all these three pins comes into the picture whenever an interrupt enters. So see, it is related with the pins, the hardware structure of 8086, and so these interrupts are known as hardware interrupts. The hardware interrupt can be non-maskable interrupt or it can be INTR, that is interrupt requesting, normal interrupt request. So non-maskable interrupts are one which we cannot mask, right? Whenever that kind of interrupt occur, obviously that will be given the highest priority. INTR is a maskable interrupt. One more interrupt pin associated is INTA, which is known as the interrupt acknowledgement pin. Now coming to non-maskable interrupt. It has a single non-maskable interrupt pin which has the highest priority than a maskable interrupt request pin, and it is of type 2 interrupt. We'll be discussing about how many types of interrupt is there in the latest sections. So whenever an NMI, that is non-maskable interrupt occur, then the following actions takes place. It completes the current instruction that is in progress, pushes the flag register values onto the stack, then pushes the code segment value and instruction pointer value of the return address onto the stack. IP is loaded from the contents of the word location 0008, and this is because it is type 2 interrupt. CS is loaded from the contents of the next word location, and then interrupt flag and trap flag are reset to 0. So whenever this interrupt occur, all these actions will be taking place. Next is the INTR. This is another kind of hardware interrupt. INTR is a maskable interrupt because the microprocessor will be interrupted only if interrupts are enabled using set interrupt flag instruction. It should not be enabled using clear interrupt flag instruction. The INTR interrupt is activated by an IO port. If the interrupt is enabled and NMI is, that is non-maskable interrupt, is disabled, then the microprocessor first completes the current execution and sends 0 on INTA pin twice. The first 0 means that when INTA receives the first 0, it informs the external device to get ready. And when it receives the second 0, the microprocessor receives the 8 bit from the interrupt program controller. When this process is taking place, the following action it does. First, it completes the current instruction, activates INTA output and receives the interrupt type. Flag register value, CS value of the return address and IP value are all pushed to the stack. IP value is loaded, that is instruction pointer value is loaded from the contents of the word location, which is given by the word location into 4. CS is loaded from the contents of the next word location. An interrupt flag and trap flag is also set. Then we have the software interrupts. So we have discussed about hardware interrupts and its two types. Now we have the software interrupts. Some instructions are inserted at the desired position in the program to create interrupts. These interrupt instructions can be used to test the working of various interrupt handlers. Normally, this interrupts are denoted by INT followed by its type number. Totally 256 interrupts are there in this category. So this is the action which is taken place when an INT interrupt occurs. Now coming to interrupt vector table. Whenever an interrupt takes place, it follows the interrupt vector table. It has totally 256 interrupts available. So 8086 has 256 interrupts starting from 00 to 255. Each interrupt holds 4 bytes address. The 4 bytes is due to each vector table will carry the ISR to be executed. So that will be available in the CS and the pointer register related to CS. So that is CS and the IP instruction pointer will be holding the ISR. So see that two registers occupy these 4 bytes, and so that is why it is being given as 4 bytes. And now altogether we have 256 interrupts, and so if every single interrupt occupies 4 bytes, then we have 1 KB memory. So see 8086 has a memory of 1 MB. Out of the 1 MB memory 1 KB memory is being utilized for interrupt vector table. And when the address is being calculated, the ISR interrupt service routine is address is calculated by code segment register into 10 plus IP. Already we have discussed how to calculate the effective address in the previous videos. After this, it will execute the ISR. So out of this 256 interrupts, type 0 to 4 are known as dedicated function interrupt. Type 5 to 31 is reserved for Intel processors. Type 32 to 255 is user defined. So if we have any specific interrupts like a print or whatever base USB connecting to an USB, for all these the interrupt service routines can be used in these locations. So out of these three, first one is dedicated interrupt, that is type 0 to type 4. So dedicated interrupt, there are 5 dedicated interrupts, type 0 to 4. So type 0 is known as division by 0 interrupt. So whenever a divisor is 0, then answer will be infinity, and so at that time this interrupt occur. Then type 1 is a single step execution during the debug of the program. That is when a trap flag is set, every single step the microprocessor will be waiting for debugging. So when type 1 is executed, this process will take place. Type 2 interrupt is a non-maskable interrupt. So this is what we discussed in the previous section, right? Type 2. So type 3 is a breakpoint interrupt. So then and there, when writing a code, we'll be having breakpoints wherein at that places a compilation will be done, and it will be program will be checked for any errors, that is debugging takes place. Then type 4 is a overflow interrupt. Whenever we do operation on signed numbers, then overflow occurs. So if any overflow occur, then type 4 interrupt will be enabled. So this is all how it has been categorized. The 256, here you see first 5 is for dedicated functions. Then this is reserved by Intel, and these are used for user defined functions. So out of these interrupts, we have certain priorities being given. See, if it is 1, that is divided by 0, then it has the highest priority. And next to that, NMI has the highest priority. Then INTR3 will be having the highest priority. And finally, the priority will be given to the single step interrupts. And this is how the execution of interrupt service takes place. So when a normal main program has been run, and if any interrupts comes in between, then what happens is the next physical address to be executed will be pushed into the stack register, right? All these details, CS detail, IP, IF, TF, flag, and all these will be pushed into the stack. Then interrupt service routine from the interrupt vector table will be executed. After execution, that is once if IRET instruction has been executed, it comes out of the interrupt service routine. It will pick the next address to be executed from the stack by using pop instruction, and then will return back to its original position and will continue with the main program. This is how an interrupt service routine has been executed. This is an assessment for your understanding. Just go through it and answer this question below. And thank you.